All right, so here we are, lesson number 9, and we're moving in our unit on electromagnetic fields and gravitational fields. We're shifting from electricity into magnetism. And so in this lesson, we're going to look at magnetic theory, and we're going to talk about magnetic fields. So really, the introduction and the review of magnetic theory is going to introduce the origin of magnetic fields. And what we see right away is that magnetic fields are actually very similar to gravitational and electric fields in that they act at a distance. So you don't need contact to experience the magnetic force. It's a force that acts at a distance. All of the force fields that we've talked about so far have two objects in common. Really, there's something that creates the field, and then there's something that responds to the field. So in the case of gravity, of course, say the planet Earth would create a gravitational field, and any of its satellites would respond to it. In the case of electric fields, there's of course one charge or several charges that create an electric field, and then there's always a test charge that responds to the electric field. Magnetism is similar to that, in that basically there's some object that creates a magnetic field, and then there would be an object that responds to it. The difference is that very often we find magnetic fields just occurring naturally in substances such as iron, nickel, and cobalt, and that's something we don't see in electric fields. Electric fields don't usually occur naturally just in elements or in a macroscopic way. And magnetic forces are actually quite versatile. They can affect magnetic substances, but as we will see, magnetic fields and magnetic forces also affect electric charge. And that's going to be one of the connections between electricity and magnetism. Now, to this point, magnetic character is not completely understood. Okay, we don't understand magnetic character 100%. And what we do know, though, is that really this magnetic nature is attributed to small regions within an object called domains. And that sets up what's known as domain theory. And that all large magnets are made up of many magnetic regions called domains. Okay? The magnetic character of domains comes from the presence of even smaller unit magnets called dipoles. So within an object, there are millions and millions and millions of these tiny little magnetic dipoles, which is a north and a south pole, and these dipoles interact with their neighboring dipoles, and really when they're all aligned in the same way, we get a larger magnetic domain. And so of course we kind of, from this point we can say, oh, okay, the law of magnetic forces then states that similar magnetic poles will repel one another with a force, and dissimilar magnetic poles will attract one another with a force. And as you know, the poles of a magnet are labeled north and south, and we can draw magnetic field lines, right? Just as we can with electric fields and gravitational fields, we can draw field lines. We can also draw them with magnets as well. The nice thing about magnetic field lines that's kind of a little bit different than electric fields and gravitational fields is that we can actually map them out physically. And of course you've probably seen this with iron filings when we kind of sketch out what the magnetic field looks like. We can also simply use a compass, right, to look at the direction of the field lines, because a compass is nothing more than a small magnetic dipole that can spin around on its axis. Okay, so here's a very standard kind of diagram of a north and a south pole, and the magnetic field lines that are created. And one of the conventions that we are going to talk about at this point is that basically if we were to place the compass at different locations around this magnetic field, we'd get these kind of field lines. And one of the things that we say in convention is that field lines always point from the north to the south. So we always have a direction, we always have magnetic fields that are directed by an arrow to the south pole. So here are a whole bunch of images, three main images that really just if you do a Google search of magnetic field lines, you'll pull up these really, really nice iron filings, really, really nice diagrams, and you can kind of see the nature of what these field lines look like. In the on the left-hand side of your screen on the top, the North and the South Pole are labeled, and you can kind of see the characteristic. On the left side at the bottom, these would be, if you look at the field lines and you kind of say, oh yeah, this is very interesting, these would be two similar poles. So this would be either a south and a south or a north and a north. And then on the right side, this is of course a horseshoe magnet, and you can see the magnetic field, especially at the base, the lower part, where you have the two ends, and you can kind of see that magnetic field down there as well. Electromagnetism is something that's been studied and really looks at one of the connections between electricity and magnetism. And Hans Christian Ørsted really discovered this link between these two forces by accident. And I think the story goes that while he was giving a lecture at the University of Copenhagen, he was using a very powerful kind of electric device, and when he turned the electric device on, he noticed that his compass kind of did something a little bit weird, and he'd turn it off, and then he'd turn the electric device back on, and the compass would again do something a little bit different. And so Ørsted's principle, the principle that's named for him, basically describes the magnetic field around a straight conductor. So here, if you look at this, this is a conductor, this kind of cylinder that runs down along this axis, and there's a magnetic field, a circular magnetic field around this conductor. And Ørsted's principle says that, hey, charge that's moving through a straight conductor, so any straight conductor that has a current through it, produces a circular magnetic field around the conductor. And this discovery led us to realize that charge moving through a conductor generates a magnetic field. And Ørsted then went on to develop a series of hand signals to help predict the direction of the magnetic fields and forces. Okay, so this is basically from Ørsted's principle comes right-hand rule number 1. And right-hand rule number 1 basically is for a straight conductor, and it says that if you put the thumb of your right hand in the direction of the current, the curl of your fingers indicates the direction of the magnetic field. So if you put your right hand in the direction of the current, and of course we're always talking about conventional current flow. If we're using the right-hand rule, we're talking about conventional current flow. And conventional current flow is the flow of positive charge. Your fingers will indicate the direction of the magnetic field. Okay, so that's right-hand rule number 1. This is something that in our course needs to be committed to memory. You just have to know what it is and when to use it. Right-hand rule number 2 is similar to number 1, except that it's for a solenoid. Okay, so this is for basically a coil of current. And what this says is that if you put your curved fingers in the direction of the current running through that coil, then your thumb indicates the direction of the magnetic field. Okay, and again, we use this for conventional current flow. And so the fingers of your right hand would point in the direction as it goes around the coil, and then your thumb indicates the direction of the field. You'll notice that this diagram, which comes from your textbook, the textbook that you're using, is actually labeled incorrectly. So be very, very careful. This right here, and we left it like this on purpose so that you would kind of recognize that it is wrong in your textbook as well. Magnetic fields always run from north to south. Okay, so this is wrong, and you should make this correction right now in your notes, because this could serve as a little bit of confusion for you. So magnetic dipoles, when we look at, basically, this is a little bit more theory, so there's some theoretical things here. Basically, all of what we've talked about above has allowed scientists to theorize about where magnetic dipoles come from and why magnetic dipoles exist as always a twosome. really we haven't ever mentioned kind of where they come from, and why are some things magnetic and why are some things not. Well, it turns out, of course, all electrons have spin, and when electrons spin, they give rise to a changing electric field, right, called an electron current. And an electron can spin basically in only one of two directions. They either have spin up or they have spin down. And whenever you have an unpaired electron, and you should be thinking, oh yeah, this kind of reminds me of the Pauli exclusion principle from probably what you learned in chemistry. Basically, when you have an unpaired electron, that creates a magnetic field causing the atom to basically become a dipole. Okay? So materials then with unpaired electrons, basically materials that exhibit a magnetic field, they're called paramagnetic. And paramagnetic materials, basically you would see, and if you look at the periodic table for things that are magnetic, such as iron and nickel and cobalt, you would see that they would have unpaired electrons. They would have unpaired electrons, and that's one of the sources of this paramagnetism. Materials with electron pairs, those without unpaired electrons, are called diamagnetic. They have no measurable magnetic field because electron spins all cancel each other out. And basically what there's much more we could go into much more complexity here, but for right now all you need to know is that paramagnetic materials have unpaired electrons and they have a magnetic field. Diamagnetic have all of their electrons are paired up and they have no measurable magnetic field on their own because electron spins cancel each other out. So let's talk about this magnetic field. And we've talked about kind of what it looks like. We've talked about a few, we saw a few iron filing diagrams. But there's a couple geometries that we can use to describe the magnetic field. So just remember that the area that surrounds any stationary or moving charge has an associated electric field, right? So for any little dots of charge, we would have basically electric fields. And we can quantify the electric fields now. After the first part of this unit, we can quantify the electric field, so we can find out what that electric field is, what its size is, what its magnitude is rather. We can determine the direction of the electric field. We can really do a really good job of that, especially for point charges and for a few other very, very specific geometries. Magnetic fields exist only in the region of space surrounding a magnetic material, right? So you'd find a magnetic, in anything that's paramagnetic, you'll find a magnetic field, or you could find a magnetic field, or whenever you have moving electric charge. Okay, so it's a little bit different. There's not, if you've got a stationary electron, it'll have an electric field. But if it's stationary, it doesn't necessarily have a magnetic field. It has to be moving. Anytime when charge is moving, you'll see a magnetic field being created. So let's talk about this a little bit more. Historically, the symbol B, capital B, has been used to represent the magnetic fields. And so we've done some experiments on charged particles that are moving in a magnetic field, and so we get a couple of the following results. These are the results that we get. When I have a charged particle like an electron or a proton and it's moving through a magnetic field, this is what happens. There's this magnetic force that we find, and it's proportional to the charge that's moving and the speed that particle's moving at. Okay. We also find that there's a magnitude and direction. The magnitude and the direction of this magnetic force depends on the magnitude and the direction of the velocity and the magnitude and the direction of the magnetic field that it's moving through. So a stronger magnetic field leads to a stronger force. A higher velocity leads to a stronger force. We also find that when a charged particle moves parallel to the magnetic field, the force is zero. So there is no force if it's moving parallel. And interestingly enough, the force is always perpendicular then to both the magnetic field and the velocity. What we can summarize all this as, and we're not going to derive it because at this point there's no sense in deriving it. The derivation is it takes some pretty complex algebra, and algebra that you'll probably learn as you get further and further into a course on vectors. But the result of all of these observations up here is evident in a cross product. And this cross product is, we've seen the dot product before as a way of multiplying two vectors. The cross product is another way of multiplying two vectors. And it basically says that the magnetic force, F sub B, is equal to the charge of a moving particle times the velocity of that moving particle, and we cross that with the magnetic field that it's moving through. Okay, the magnitude is given by QVB sine theta, and these two formulas right here really give us the definition of what that magnetic force is when a particle is moving through a magnetic field. Magnetic field is always measured in units of Tesla, okay, and 1 Tesla is defined as 1 Newton per coulomb meter per second, okay. If instead of having one little charge or one little particle moving through a magnetic field, let's say we have a current that's moving through a magnetic field, then we can take the expression that we had above, the magnetic force is equal to Q times V with the cross product of the magnetic field B. We can actually extend that and we can say, okay, well, the force then that exists on any conductor, straight conductor, that carries current I and has a length L, that the force is IL cross B, or ILB sine theta if you want just the magnitude. And so this formula right here is going to help us do a couple examples as you're going to see in a few minutes. Why is any of this important? Well, it's because there's magnetic fields all over the place. And if there's magnetic fields all over the place, anytime when a current is cutting through a magnetic field, there's going to be a force that's present. And to be able to determine how large that force is really, really crucial. Right-hand rule number 3 will help us to predict the direction of the force. And so this is the third and final right-hand rule, and it's different than the first two because the first two really just talk about a current that creates a magnetic field. This one talks about a current that cuts through a magnetic field, giving rise to a force. And basically it says that if you place your fingers in the direction of the magnetic field, with your thumb directed in the direction of conventional current, your palm will indicate the direction of the force. Okay, and you can see that in this little diagram right here. Okay, so here's an example. A wire is carrying a current of 10 amps and is suspended between a house and its garage 5 meters away and in the I-hat direction. If the Earth's magnetic field in this region happens to be straight down, so in the negative j-hat direction, and has a value of 5.0 times 10 to the minus 5 Tesla, what's the magnitude and direction of the force on the wire? All right, so here's our little diagram of our house and the garage, and here's a wire that's running from the house to the garage. So it's 5 meters long, and the current would flow from the house to the garage in this case. And so what we know is that we know the current and its direction. We know how long the wire is. We also know what the magnetic field is, and it happens to be straight down. So we can find the magnitude of this magnetic force by using this formula. And because the current, which is I hat, and the magnetic field, which is downwards and negative j hat, are basically 90 degrees apart. They're perfectly perpendicular. then we can simply add all of this together, and we can say, okay, well, here's the magnetic field B, here's the current I, here's the length of the wire, 5.0 meters, and here's the sine of 90, because the angle that's in between I hat and J hat is, of course, 90 degrees. And what we end up with is 2.5 times 10 to the negative 3 newtons. So not very much force at all. What direction is this in? We're going to use the right-hand rule. And if you put your fingers in the direction of the current, fingers in the direction of the magnetic field, your thumb is in the direction of the current, your palm gives you the direction of the force. Okay, and in this case, your palm would point into the page, and that is the direction of the force. So the magnetic force in this case is 2.5 times 10 to the negative 3 newtons directed into the page. Let's take a look at some of the sources of magnetic fields at this point. So we've looked at the magnetic force and kind of how to define that. We also know that moving charges create magnetic fields, but really, let's take a look at some of the factors that affect the strength of the magnetic field around a conductor. Okay, so determining magnetic field strength for general configurations, you know, for weird geometries or for weird shapes, if we've got currents that are in, you know, a ring, or currents that are in a loop, some of that takes some pretty heavy duty calculus, but we don't need to worry about that if we look at some very specific configurations where the calculus kind of is done for us. And so to be honest, there's really only three that we're going to look at in grade 12. Okay, so the three geometries that we're going to look at would be a long straight wire, okay, a flat loop, and a solenoid. And we're going to look at the magnetic field and how big it is and what it's all about for these three different geometries. Okay, so let's take a look first at the infinite wire, which is basically a really long straight wire. And we're going to look at the magnetic field at some point a distance r away. And this could be above, it could be below. It's basically some point around here, because we know from right-hand rule number 1 what the magnetic field is going to look like. We could sketch it out, but we'd like to have a way of calculating a value, so how big it is. And so what we say is that the magnetic field around a straight conductor has this form. Okay, so the magnitude, so that's great because we can now find the direction from the right-hand rule number 1, but we can write the magnitude now as mu I over 2 pi r. Okay, let's define what these are, because we're introducing a couple new things here. To find the direction, use right-hand rule number 1. So mu is a constant. Okay, so it's just like when we were doing electric fields, we had K. When we were doing gravitational fields, we had big G. Mu is a constant. It's the permittivity of free space, or the magnetic permeability, excuse me, is the magnetic permeability. I is, of course, the current that's flowing through this wire. And R is how far away the point is that you want to find. So obviously in this case, as R gets bigger, the magnetic field gets smaller. And so the farther away you go from the magnetic field, the farther away you go from the wire, the smaller the magnetic field gets. So magnetic permeability is a constant. It's very readily found in your textbooks, and you'll see an example of how we use it in a moment. Different substances have different magnetic permeabilities. For the most part, we're going to be finding the magnetic field in a vacuum. So you really, even though it's got different values in different substances, in this course, you won't have to worry about what those different values are. We're just going to use one value for almost everything. Mu is basically, it's another one of these measures that's specific to a substance, right? And what it measures is it measures the substance's ability to allow for a magnetic field. So things that are really magnetic field friendly will have different values than things that aren't magnetic field friendly. And so that's what mu characterizes. Again, it's just like a constant for the material through which the magnetic field is acting. Our next geometry is a loop. So if we take a straight conductor and we curl it up into a loop, one flat loop, then basically what we get, the magnetic field strength at the center of that flat loop, is mu times n times I divided by 2r. Okay, so we don't have to just have one turn. We could have many, many, many turns, right? And that's what n is. So the unknowns here, mu is again the magnetic permeability. N would be the number of turns of this wire. So let's say I coiled this wire 5 times. Well, that n would be 5 in that case. I is, of course, the current going through the wire. And 2r, r is, of course, the radius of the loop. To find the direction of this magnetic field, use the right-hand rule number 2. Last but not least, the solenoid. Okay, and the solenoid is basically a stretched out curly Q here. And the radius is, of course, right here. It's basically the radius of these loops. I is, of course, the current, and L would be the length of the solenoid. And the formula that we're going to use here is B equals mu Ni over L. Okay, and so basically along this center point in the solenoid or anywhere inside the solenoid, mu Ni over L is the formula that we want to use. Again, mu is the magnetic permeability, N is the number of turns, I is the current, and L is the length. So now that we've seen these, let's actually take a look. Oh yeah, you'd use right-hand rule number 2, by the way, to find the direction of this. So let's take a look at an example. A long straight conductor is coiled once into a flat loop, and it's got a radius of 3 centimeters. If the wire carries a current of 1 amp, find the magnetic field at the center of the loop. Okay, so here's mu. It's 4 pi times 10 to the minus 7. Again, this is the constant that we're going to use for the most part all the time. And it's because this is what it is at the center of a loop. And we're going to say there's nothing in the center of the loop. It's just a vacuum. I is 1 amp. The radius is 3 centimeters. And there's 1 turn. It's coiled once into a flat loop. So B is equal to mu times N times I divided by 2R. We can simply make the substitutions that we have. 4 pi times 10 to the minus 7. 1 times 1 divided by 2. This right here is 0.03, by the way. 0.03. And so basically you get 2.1 times 10 to the minus 5 Tesla. And if we use right-hand rule number 2, and we say, okay, the current is in this direction, we would say that the magnetic field would point out of the page, because if the current goes in here and comes out here, then this loop right here would have a magnetic field out of the page. Okay, here's another example. Find the magnetic force on a wire carrying 3 amps of current from a second wire carrying a current of 9.5 amps at a distance of 1.4 centimeters. So what we need to do, we've got these 2 conductors here. All right. So we're going to assume the length of both is about 1 meter long, no problem. And so here's our 2 conductors. I've got one, the guy that's feeling the force. We're trying to find the magnetic force on this upper wire. So what's this going to do? Well, this guy's got a current, it's 3 amps, it's in the I-hat direction. And this guy right here, this is the one down here that's creating a magnetic field. And so basically we get 9.5 amps, it's also in the I-hat direction, and they're 1.4 centimeters apart. So this guy's creating a field, this guy up here is sitting in it, and we want to find the magnetic force on him. Conversely, we could also do the same with the other. So this one creates the field, the upper one responds to it. So there's 2 steps to this. First, we have to find the magnetic field from this second wire, this wire down here. So let's do that first. It's a straight conductor, so we say mu I over 2 pi r. We make our substitutions and we solve. and we say that it's 1.36 times 10 to the negative 4 Tesla, and that's directed out of the page because, of course, it's a circular magnetic field, but up here in this region, right, because it's 1.4 centimeters away, the right-hand rule number 1 tells us that, okay, if we put our thumb in the direction of that 9.5 amp current, up here, the magnetic field directly above it is out of the page. Okay, so we used right-hand rule number 1 to solve that. Now, we want to say, okay, well, I know the magnetic field where this guy is sitting. It's out of the page and it has a magnitude of 1.36 times 10 to the minus 4. So now I can say, oh, well, my magnetic force is equal to I times L times B times the sine of the angle in between them. And so I can say, okay, the current in this upper wire is 3 amps. The length of it is 1 meter. I know the magnetic field, and I happen to know the angle in between the current and the magnetic field is perfectly perpendicular. It's 90 degrees. And when I make this calculation, I get 4.1 times 10 to the negative 4 newtons, and it's directed down. I used right-hand rule number 3 to solve for that, and I get a force of down. So basically, these two wires are going to be attracted to each other. The upper wire is going to feel a downwards force towards the other wire.